Okay, so I welcome you all to this plenary lecture at the HEM. I would first like to remind you of the practical setup. You can ask questions, but only through the question and answer button at the bottom of your screen. And then I'll pose the question for you, or in exceptional cases, I may give you the floor and you can actually talk yourself. I'd like to save the questions till the end of the lecture. There will be plenty of time to ask questions then. Then next, it's my pleasure and my honor to introduce our speaker, Peter Bühlmann. Peter is Professor of Mathematics and Statistics and Director of Foundations of Data Science at ETH Zurich. He's strongly connected to ETH Zurich. He also did his studies there, undergraduate, and he got his PhD there. And he was chair of the Department of Mathematics there from 2013 to 2017. In between, he was a postdoctoral fellow and a Neyman professor at UC Berkeley. Peter received many honors. I just mentioned honorary doctorate from the Université Catholique de Louvain, the Guy Medal in silver from the Royal Statistical Society, and others. Among the important lectures he already gave are the Neyman Lecture of the Institute of Mathematical Statistics, the Rothschild Lecture at the Newton Institute in Cambridge, a section lecture at the International Congress of Mathematicians in Rio de Janeiro, and an invited lecture at ICAM in 2019. Peter served the community in many committees, program committees, and other committees. I specifically mention that he was the co-editor of the Annals of Statistics from 2010 to 2012, the prime journal for mathematical statistics. Peter's research is in the exciting interface between statistics and computer science, statistical learning in a broad sense. In his early work, the analysis of machine learning algorithms such as boosting, bagging, the bootstrap were prominent and influential. Later work features methods for variable selection in high-dimensional regression and graphical models, such as come up in biological and genetic applications, where he also worked together with subject matter scientists. In the last 10 years, he has made fundamental contributions to causal inference, particularly in high-dimensional models, which again is at the interface of statistics and machine learning. Peter wrote many very well-cited articles. He also co-authored with Sarah van der Geer a book on statistics for high-dimensional data. It's called The Bible on the Mathematical Theory for the Lasso and Other High-Dimensional Methods by some. Today, Peter will talk on statistical learning, causal-oriented and robust. And then I'd like to give the floor or the screen to Peter. Peter, please.
Okay, so thank you very much, Art, for this nice introduction. It's a great honor also to give this lecture, and I would like to express my sincere thanks for the invitation. And I would also like to really spell out a big thank you to all the organizers for actually making this Congress possible under the difficult circumstances. I would also like to acknowledge at the beginning of my lecture the main collaborators for the research I'm presenting today: Dominik Rothenhäusler, Niklas Pfister, Jens Chen, Jonas Peters, and my colleague at ETH Zurich, Nikolai Mainshausen. So my talk has the word statistical learning in the title, and there is this absolutely wonderful book published a bit more than 20 years ago by Hastie, Tibshirani, and Friedman, The Elements of Statistical Learning. And these people have really built a bridge between statistics and machine learning. And the book is, among others, really a basis, a fundamental basis of the success of statistics and machine learning, say, during the last 20 years, which is truly exceptional. However, the book has nothing on so-called, in my view, open issues on stability, robustness, generalizability, and transferability to new populations, and insight and understanding in terms of causality, which is truly a dangerous word. And I want to highlight some aspects a bit here today in the lecture to make statistical and machine learning more causal oriented and more robust. So as you all know, nowadays we have multiple of terabytes of data, a huge amount, and we want to extract something useful. We want not just black boxes, we want to understand, we want to get new insight. And some people call this nowadays interpretable AI in modern language. Some people call it interpretable machine learning. And I also sometimes call it just interpretable statistical inference in modern context. As I will argue, this kind of better understanding, more insight, actually exhibits increased robustness. This is maybe no surprise in vague scientific folklore terms. If you understand the system well, it's probably also more robust, but this needs to be mathematized, and this is what I want to explain and show you a bit today. So let me set the scene first. As we have seen also in this COVID-19 crisis, I think data as numbers alone, they're usually not very informative. But the point is, of course, data as numbers in the context of mathematical models can truly be very highly informative. And so here is the statistical way how we deal with data. We think of a data generating probability distribution, and then we do corresponding statistical inference. And I'd like to quote here from Mosteller and Tukey, 1968. One hallmark of the statistically conscious investigator is her or his firm belief that however the survey, experiment, or observational program actually turned out, it could have turned out somewhat differently. And so there is kind of noise, there is randomness, and this is kind of the statistical framework. What we do, we have data, we have numbers, and we interpret these numbers, little z1, z2, zn, as outcomes of random variables, cap z1, cap z2, cap zn. These random variables, in the simplest case, they are maybe IID, independent, identically distributed, or maybe from a stationary distribution. And this data generating distribution is denoted here as P0. So there's an underlying data generating probability distribution P0, which kind of generates the data. This can be from a possibly infinite dimensional model. And that is the setting we're looking at. Now, the goal in statistics is inference from data about a functional of this data generating distribution P0. And of course, this has a huge, long history. I start here with Grant and Petty, 1662. They kind of brought out a first real good analysis of a life table. And then there are lots of other names, famous names here, who contributed to this program here. Most of this is about generalization to new data, to new individuals from the same distribution P0 as the observed training. So, for example, it is about a new patient who has the same characteristics as in a representative study. That is the classical framework. What I want to talk today is generalization to new data generating distributions. The classical framework does typically not allow to generalize beyond the data generating distribution P0, which you observe in the data. So what I want to do now, the setting is as follows. So we have data, we have observations from a data generating distribution P0, but I want to say something about a new distribution P prime, which is different from P0. Now, of course, this is a very bizarre problem, right? This cannot be answered in general. This is very ill-posed. Nevertheless, people have studied that problem since quite a while under the names of transfer learning, domain adaptation, transportability, and so on and so forth. So actually what I want to do here and want to explain today is a bit more general and often more realistic setting. What we typically observe nowadays in large-scale data is heterogeneous data from various distributions data generating distributions PE. And this E is an index in a space script D, and it is the index for an observed environment, a scenario, a certain subpopulation. And the point is, typically we collect now data across many subpopulations, and this is indexed by E in this script D. And again, I want to say something about a new PE prime where the subpopulation E prime has not been observed in the data. So this is a bit more the general problem than just before. Okay, so there are very many examples out there. You may wonder, why is this interesting? But here is a first little example. For example, you can look at multi-center studies, say, of the effectiveness of COVID-19 vaccine. And you do this study with diverse subpopulations in different continents, in different countries. But typically, you want to generalize to new, different, outside the study subpopulations. It's very common that you want to do this. You want to know whether the vaccine is effective also for people who have not been tested. And I'm quoting here from Dahabre et al. Instead, for decision-making, the users typically have a new target population in mind. So here's another kind of cartoon example. This is a self-driving car, an autonomous system. I'm not working on this problem, but what people do is they train the system on designed scenarios from this E, very different, very many scenarios, maybe 100 different scenarios. But you want to generalize to a new scenario, E prime, which has never been observed in the training phase. And the system should also perform well on these new scenarios. Okay, so if you ignore this generalization issue to a new P prime, which is different than your data generating distribution, in many realistic applications, machine learning algorithms will have very, very poor performance. This is well known for the experts. I have listed here a couple of issues. And I should also point out, standard machine learning often performs extremely well on new data, which comes essentially from the same distribution as used for training. So you keep that in mind. It's great for, say, image classification for same type of images, speech recognition for similar same type of persons. But if you generalize to different populations, it can fail massively. Okay, so how can we try to do this generalization to new populations, to new environments? And so here is kind of the framework I'm using. And it's kind of a model for the entire system and also a model for the perturbations which create these different subpopulations. What I have in mind is a responsive target variable Y of interest. I have many features, we call them also covariates, explanatory variables, they're denoted by X. And there are also many non-observed hidden variables in the game. That is reality. And the truths may look like this. This is the oracle world. This is my variable of interest. This would say, I mean, you read this diagram, Y is directly influenced by X1 through a function, X2 through a function, and it kind of influences X3. And Y is also influenced by a hidden, unobserved, potentially confounding variable H1. Okay. So what you observe is typically this. Of course, you don't observe the hidden variables. You just observe Y and your feature variables X1, X2, X3, and you observe a lot of dependence between these variables. For example, if you measure correlation, typically every variable is correlated with every other one. Even if you look at partial correlations, you see very strong regression associations between the variables because it's spurious, because you don't see the hidden variables. And also, what you don't have as an information, you will not see any directionality. Now, what is the very ambitious goal? The very ambitious goal in causality would be, given data, please give me the structure of the problem, find out that X1 is a parent of Y, X3 is a descendant of Y, learn these edge functions, even in presence of hidden variables. This is a very ambitious task. People have worked on this problem, including myself. Just to make the point clear, this cannot be solved by regression or standard machine learning. Standard machine learning doesn't give you the directionality. here's a related problem, which I find personally a bit more realistic. Maybe I just want to do prediction of y given my feature variables. I don't know the directions, but I want to make the prediction robust under various perturbations across various subpopulations. And a bit surprisingly, these two goals, actually, they will have something in common, which I will explain today. So what is mathematically behind these models? So typically one looks at one way is you look at so-called structural equation models. So you have a structure in terms of a directed graph. Here for simplicity, it's a DAG, it's acyclic, but that's not an important assumption. And once you have the structure, you can specify function models for these different random variables in the graph. So my notation is W includes all the random variables, and every component here is modeled as a certain potentially nonlinear function of the parental variable comma error term. So y would be modeled as a potentially nonlinear function of x1, x2, and the hidden variable h1, comma error term. You do this for all the variables in the system, and you make this assumption that these stochastic disturbance terms, they're jointly independent. Now, Pearl calls this structural causal models. It just makes this somehow huge step to say, well, this is my true underlying causal influence diagram. Well, this is a certain kind of philosophical argument. I rather stay with structural equation models, but mathematically, these are exactly the same thing. It just matters whether you claim that this is the true causal system or not. It's a bit of a philosophical issue. Okay, so we have these function models for every random variable. So these structural equation models, we have the joint independence of these stochastic disturbance terms. And then one can derive that the joint distribution of all these random variables in this model, they satisfy certain Markov properties with respect to the graph structure. This has been beautifully pioneered and formulated by Lauritsen, Stefan Lauritsen, and he wrote it down also in his famous book in 1996. That is one important side remark. Now you could have the idea, okay, maybe I have a lot of data, kind of observational data from P0. Let's try to learn this structure from the data. And that is, of course, a very ill-posed problem. It's impossible in general without any additional assumptions. And the assumptions are very non-testable. It's very well known that one can only estimate a so-called Markov equivalence class. And what it means is, given a data generating distribution P0, given a lot of data from that distribution, several DAG structures, several graphs, and corresponding function models generate that P0. And as a consequence, this means that learning directions, learning causal relations just from observational data is very troublesome. But this kind of framework is kind of very useful to do something in addition. This is useful to also now present a model for what the perturbation is. And I just want to give you a very simple introductory example. It's actually a famous model. It's Pearl's do intervention. It's a model as an example how we model perturbations in the system. So here is my DAG, my graphical structure. Here's the corresponding structural equation model. And now I make an intervention, a perturbation, and the intervention is written as do x2 little x. What that means is you set the value of this random variable to a number little x. Okay, so you can look in the graph. What you do, you just replace x2 by this value little x. Of course, this arrow here will be deleted because it's an external intervention you do. X3 has no effect on that anymore. So this is again a graph, and you write down the corresponding structural equation model. So what happens here, there are two things, that this intervention value here propagates dynamically through the system. If I set this variable x2 to little x, it has an effect on x1 and on y. And the other thing which is important to note is I take the same functional models here, except for the second equation, but I keep my f1, I keep my fy. And so these are the two big assumptions or properties. The first one is kind of a good one. There's a dynamic propagation of the intervention through the graph. And the second one is kind of a huge assumption. The functions here stay the same in these structural equations, despite the fact that you do an intervention in the system. So there are many other perturbation models based on structural equations, additive shifts, and so on and so forth, but all of them exhibit dynamic propagation of that intervention. If I change a variable, others will change. And this big assumption that at least parts of the structural equations remain the same. This is a huge assumption. It's called the autonomy assumption, but you have to make an assumption. Something needs to remain the same. Otherwise, you cannot really extrapolate to a new subpopulation, to a new scenario. Okay, so this explains maybe a bit why causal thinking can be useful for generalization. With such perturbation models at hand, causality is actually giving me a prediction, a quantitative answer to a what if I do question. What would happen if I make an intervention at the second variable? And that intervention is not observed. So Judea Pearl did very fundamental path-breaking work in this area, and also he wrote this important book. And I really want to point out that he made this very clear that this is maybe the main task of causality, to give a prediction to a what if I do question. It also goes much further back. I want to come here or reference to Jerzy Neyman. Already in his master's thesis in Poland, actually in 1923, he created this potential outcome model. What would have happened if we would have assigned a certain treatment? It's a very bizarre problem, right? But Neyman came out with a model, it's called the potential outcome model, and it really became a milestone. So just to make the point clear, many modern applications are faced with such prediction tasks. This is one I'm personally working on, say in genomics. We would like to answer the question, what would be the effect if I manipulate a gene on the growth rate of a plant? And I want to predict this effect without having any data on such a gene manipulation. Advertising in e-commerce, what would happen if you show an advertisement, policy making, algorithmic fairness, and so on and so forth. They all go on this potential outcome model. And therefore, causality can also be used to generalize to new scenarios. What would happen for a new patient who is different, who is a perturbed version from the ones in the study? Let me exemplify this a bit graphically with really a toy example, but maybe you remember this after my talk for a while. So can we predict an intervention effect? This is synthetic data. I have an X variable, a Y variable. I made it up. So they have a strong, nice regression dependence. There's correlation. You can fit a linear regression line through the data. Very standard elementary textbook. Now I manipulate X and I set X to the value, say -8. And I ask, what would be the prediction for Y under this manipulation of X, setting it to -A? Give me the best prediction of Y. Okay, you can think quickly about it. And many of you say, well, this is the solution, right? This is the best prediction on the regression line. That's textbook. And that's the right answer if X influences Y. If X influences Y and you manipulate X, then something happens to Y, and this something which happens to Y is exactly according to the regression line which you have learned from the data. Others might say, well, my best prediction for Y is this one. If actually Y would kind of directly influence X, if I manipulate X, nothing will happen to Y, and my best prediction of Y is just the mean of Y. And the challenge is, given data, how can you make the prediction whether it should be here or there? So it's really the directionality here which matters. Now, this is toyish, but this is actually real. So this is something we have been working on. So this is kind of predicting gene knockouts. What you see here in this plot are expression variables or measurements of genes. So we have lots of genes in the game, and I just show you two-dimensional plots. I show you an X gene, a Y gene, certain expression values, activities of these genes, and you observe the blue data cloud. You fit a regression line as before. Then you do in the lab, you make a manipulation of the X gene. It has kind of, you shut down the effect of the X gene, and lo and behold, the Y gene actually changes roughly according to your estimated regression line. And this is the other example. You have an X gene, a Y gene, you observe the blue data cloud, you do a manipulation in the lab, you knock out the gene, and nothing happens to the Y gene. And without doing this experiment, how could you predict this? And we have some results, which I will indicate a bit, and I will try to explain a bit that we actually can make this prediction, at least to a certain extent. So the word causality is really overly ambitious. I repeat myself, but I think it's important. It's really about predicting intervention effects. What would happen if you would perturb, if you would assign, if you would do something, and you have never seen this perturbation, this assignment. So this is a short intermediate summary. We have a mathematical model. Pearl calls it causal. That's not so important. We have a mathematical model, an intervention model, and with these two things together, we can predict intervention. I can make this extrapolation depending, of course, whether the model is good or not. Now, what I want to do is, well, maybe I have seen already some interventions in the data. Can I infer from this back to the system? And this is what I want to explain next. So this is heterogeneity, robustness, and a bit of causality. Now the setting, a bit as described before, I assume heterogeneous data from different known, observed, maybe environments, experimental conditions, perturbations, or subpopulations, whatever you think it's more appropriate, and this is always indexed by little e in this space script e. So I have a regression classification type problem. These features X, response Y, they have a distribution P, and everything is indexed by the corresponding subpopulation. So examples again, I could think of script E as having 10 different labels. It could be 10 different countries. I see 10 different subpopulations. I could have medical data from 13 different centers or hospitals, and many large-scale applications are of that sort, where you have different subpopulations. Now I consider many possible, but mostly non-observed new subpopulations, new perturbations from a space script F, which is typically much, much larger and contains the observed script D. Examples from before, script F could be the 10 countries, which I have in the data set, and maybe all other countries in the world, or the 13 centers, hospitals, and maybe many new centers. And so here is the pragmatic problem. It's just a prediction problem. Predict Y, given the features X, very standard, right? Such that the prediction works well, is robust for these many possible new environments, E from this space script F on new subpopulations, based on data from much fewer environments or subpopulations. Okay, so you want to make a prediction which works well on future perturbations. Here's again the problem. And let's just look in this talk only or mostly at linear models. You can mathematize this, and you can look at worst case risk, L2 risk, right? Expected value of Y minus XE beta, though this is multivariate. I look at worst case over all perturbations, all subpopulations from this space script F, and I want to find a regression parameter which optimizes this worst case. People call this robustness. And I also refer it to causality because it's something about a new scenario, a new perturbation where causality could give an answer to. So these things actually belong together, and this has not been known for quite a long time. This is quite recent. Causality and worst case risk over perturbations, they belong together. For linear models, again, only in a nutshell, if you look at optimizing worst case risk, this is what people call the causal parameter. Now, the point is, of course, what is the worst case risk? What is descriptive? What is the mathematical description of descriptive? And I'll explain in the next slides. But this is an important message. Risk optimization all of a sudden corresponds to causality. Okay, so here are the results which we have, and I'm not going too much into details, but let me explain here a first one just roughly. If you define your descriptive, the future perturbations, they're all possible perturbations on your random variables which do not act directly on y, but dynamically propagate. So here's the picture. I have an x-y relation. This is multivariate. I have kind of environments, subpopulations. They change x, but they do not act directly on y. Then this holds. Worst case risk optimization over all these perturbations which do not act directly on y. This gives me the causal parameter, and the causal parameter is in my structural equation model. So y, everything is linear here for simplicity, is a linear function of the parental variables, and that regression coefficient is this beta 0. Sometimes I call it also the internal systems parameter. For the experts, they say, well, this holds also here. And it's kind of an interesting message. Even if you have hidden, potentially confounding variables, if you have f, all perturbations which do not act directly on y and also not on h, the same holds true as well. Okay, so causality and distributional robustness, they're actually intrinsically related to each other, and that's not a new thing. This has been formalized by a person in economics, Trygve Havelmo, who later got the Nobel Prize in economics in 1989. Now, Havelmo, already in 1943, with very different kind of terminology and formalism, implicitly had this, what I reformulate. He said, okay, if we take this causal parameter, say in this structural equation model, just the edge weights, if we look then at the residuals and the distribution of these residuals, when I just plug in the causal parameter, these residuals remain invariant across all possible perturbations which do not act directly on y. So Havelmo knew that causal implies a certain invariance. That is an important step. So with nowadays data, we thought, okay, well, maybe we can observe invariance in large-scale data and just go backwards. Surprisingly, nobody really has done this before. And so this was our attempt. And so the idea is kind of very simple. We say, okay, let's just search for invariance in the data. So we can do this, say, with statistical testing. We test for potentially high-dimensional regression parameter beta star, such that the residuals remain invariant over all the environments, all the subpopulations which you see in the data. And now you can prove that if you see enough perturbations in the data, then, and under some additional conditions, then beta star actually gives me this causal parameter. Now, this kind of completes a bit the way backward. If we search for invariances in the data, indeed, one can say something about the causality in the system. That's very ambitious because it needs additional assumptions, but at least we can enhance robustness. So we call this inverted process invariant causal prediction, ICP. It's statistics. We know how to do error control on these things. So for example, we can have a statement under some conditions, the probability that you make at least one false positive claim, you claim a causal variable, you can control it by a value alpha, and you can set alpha to say 0.05. Now the question is, well, these assumptions which I have not explained here, does this all make sense in reality? And we actually have quite interesting results in gene network analysis of yeast, which were biologically validated. I mean, this extrapolation always depends on assumptions, and the question is, are these assumptions approximately reasonable in reality? Let me just expand a bit on this problem. So actually we have gene expression measurements in yeast. This is baker's yeast, which you use for the bread in the morning. You have a bit more than 6,000 genes involved. You measure the activities of these genes. we have 160 observational samples of wild type, just non-perturbed yeast. And then there are already a lot of samples where we perturbed, the biologists perturbed one of the genes. So they knocked out a gene, they knocked out another gene. So they knocked out already 1,479 genes. Now, in a nutshell, what we do, we fit this invariant linear model with this ICP. It's just linear, but invariant across these interventions. And then we rank the importance of the genes according to p-values. We have statistics, right, for invariance. So I have a p-value for invariance. One gene is the response, all others are the features. And in normal language, what we do is the observed gene knockouts, which we have, they are used to predict the next ones. Now we can validate. We actually put a third here aside, so we train only on roughly 1,000 interventions. And then we want to see how well we do in predicting these gene knockouts. And that was the picture from before. So this is an ROC type plot. On the x-axis, you see the number of prioritized predictions. This is the top priority gene intervention effect from the model, the second top, and so on. And on the y-axis, you count the number of true effects. You can validate, right? You validate outside the data whether it was actually a true effect. So you really play this game, you see the blue part, you do an intervention and you want to predict whether it was here or there. And this invariant methodology produces at the very beginning always a right answer. Then it levels off a bit. So the sixth one is wrong, the seventh is right, this is wrong, then it's right, and then it becomes very difficult. It's a very hard problem, but we can indeed have some success in making this prediction whether it should be here or there. So why is this useful? Now you can prioritize future experiments, right? Now you have a computer, you can just ask, well, what will happen if I knock out this gene? And it gives you an answer. And it has been validated to a certain extent. So let me also move now a bit further to what we call causal regularization. So I tried to emphasize the importance of this invariance, but this is maybe too crude, right? To have things exactly invariant. And so here is an idea to make various degree of invariance from small to large. So you want to have kind of residual distributions, maybe a bit invariant, more invariant, and so on and so forth. The environments, the subpopulations E from this space script E, which you observe, they are now outcomes of a random variable, which we call an anchor. Just a switch of terminology. So how would you try to make residuals a bit more invariant? So here's an obvious idea. You try to estimate your regression parameter by minimizing residual sum of squares. And then you penalize, you regularize such that the inner products between environments, this is my variable A, and the residuals become small. So large inner products are penalized, large empirical correlations are penalized. That obviously makes it fairly invariant. So this is the thing, the proposal. This is not quite what we do. This is a bit technical here. We look at this pi A. This is the linear projection on to the column space of A of this anchor variable, which produces or generates my environments. And I propose, or we propose this, what we call causal regularization. It's a very general principle. You just minimize the regression parameter with anti-projection length squared plus a regularization parameter times projection length squared. Okay, this is just a proposal. For gamma equals 1, this is least squares, right? Because least squares can always be decomposed in anti-projection length squared plus projection length squared. And for general values of gamma, we call this general regularization. Now you say, oh, okay, this is just a simple linear model. You can, of course, in higher dimensions, you can add, say, sparsity enforcing regularizers like L1 norm or other penalties. This all is an easy convex optimization problem. You can even go further and say, well, I do this with deep neural networks with random forests. I just do this in the nonlinear world. I just minimize over my function space anti-projection length squared plus gamma times projection length squared. And let me just briefly relate to Alfio Quartarone's first plenary talk of this conference. For example, you could use his nice physical heart model. So there's an additional term, and I can just add additional invariance to such a model as well. So this kind of principle can be used to add invariance to a broad class of mathematical models, and perhaps in some applications, this is a good idea. So what is it doing for us? Why should we go with this causal regularization? It actually has kind of interesting mathematical guarantees. The question is, if I have my environments or this anchor variable A here, how does it act on the system? What is the perturbation model? So I have a multivariate X, I have a Y, I have hidden confounding variables. And the question is, how do I model? How does A act on the system? I showed that before. If the environments act only on X, but not on Y and not on H, this is a very well-known model. It's called the instrumental variables regression model. It's very popular in economics and econometrics. So there's a huge assumption of this kind of model, namely that it acts only on X, but not on H and not on Y. So how the heck would I know that my environments would not act on a hidden variable, and I cannot even name what the hidden variable is, right? So this is a big assumption. So we say, well, this is too unrealistic. Let's just assume these environments, they act potentially on all the variables X, Y, and H. We allow for feedback loops here, but we make one assumption, namely that these environments, they're kind of external. They're just source node in the graph. And that is the reason why we call this anchor. It's a source node in the graph. Okay, now you have a structure. Now you put a quantitative model on the structure. For simplicity, it's linear. And so I have a linear model on that structure. I have an error term, and I have this kind of exogenous additional term from the different environments as an additive shift M times A. Well, we allow that A acts on Y and H. That is a fundamental issue because now I cannot identify this parameter any longer. And people say this is crazy, right? You cannot do that. You cannot identify the parameter. That's true. But as I will just explain a bit, this causal regularization still solves for optimizing a worst case risk over a certain class of perturbations script F. Okay, let me explain this a bit. So we have this model for my heterogeneous data. It's linear. It has a stochastic disturbance term. It has this additional exogenous term M times A. This corresponds to my observed different subpopulations. Now again, I need a model for the future perturbations. And the model is, okay, I say there are just shifts in the future, shift vectors, V, they dynamically propagate through the structural equation as before, the stochastic error term, but the V here cannot be arbitrary. Here the V is in a certain space, C gamma, that's technical, but what's important is the V is in the span of M, in the same direction as M. So in folklore, we model the future perturbations that they have the same direction than what we have seen in the data, goes the same direction, but it's potentially much longer, much stronger. This is maybe the most natural extrapolation. How would you extrapolate otherwise? I see kind of interventions, I see perturbations in certain directions, and I model that it continues more or less in that direction. The more perturbations also and heterogeneity you see in the data, the better you can extrapolate. Why? Because the span gets larger. And that is very controversial at first sight in classical statistics, where you want to have nice, clean data. But I argue, well, if you see a lot of heterogeneity, this has fundamental consequences for robustness. And so here is actually a theorem which makes this more concrete. This is just for the infinite sample version to make this a bit simpler. So this pi a becomes the population prediction. It's just the conditional expectation given a. And the duality kind of reads as follows. For any beta, I can look at a worst case risk here under this perturbation class, which I just introduced. And this equals exactly my objective function in causal regularization, namely anti-projection length squared plus the regularization parameter gamma times projection length squared. And this gamma here actually is corresponding exactly to the size of these perturbations. So Ad, you have raised your hand. Okay, so it's fine. So the point is here, worst case shift interventions actually correspond to regularization. And the idea is now, well, just regularize. This is easy to do. This is a convex problem. And this is maybe a bit a surprising story, and it's not long known that robustness and causality through this causal regularization, they're intrinsically related with each other. And I have listed here a couple of names. Of course, many others have contributed to either the left or the right-hand side. But the things are really connected. The kind of contributions are connected through the framework which I just explained. Let me make this a bit more, again, kind of showing this to you from a different angle. So we have this worst case risk from this causal structural equation model. And distributional robustness typically looks at this. You look at a worst case risk over distributions with a certain metric. So P0 is the observational distribution, it's a steady state, and then you choose a certain metric. Now, in a very simple case where we say my anchor regression model is Gaussian, then this metric, this problem here corresponds to a metric. This is Wasserstein between Gaussians, but with interventional data-dependent covariances, potentially degenerate. So kind of in ordinary language, we learn the metric from the observed perturbations. And this is especially useful in high dimensions. So here's the picture. Distributional robustness, you postulate a metric and then you have a sphere, whereas this causal regularization learns the metric with kind of an ellipsoid here, and maybe it is degenerate in certain directions. So the things kind of belong together. The mathematics allows to classify equivalences and differences. And I believe this can actually be exploited for better methods and algorithms, taking the good from both worlds. One indeed can improve prediction with this causal regularization. People have started this since quite a while. Leon Baudou in 2013. There are quite some successes now that you can robustify your neural networks, your machines, to make it more robust, and they actually do it through this causal lens. I'm also very interested in the interpretation because science aims really for causal understanding. And as we just talked a bit, this is a bit ambitious. Causal inference necessarily requires often untestable additional assumptions. Like in my anchor regression model, you cannot identify the causal parameter. But what you can do is you can still do this causal regularization, and you can look at this parameter for a certain value of gamma, beta gamma, which optimizes my causal regularization risk or objective function. And if I push the regularization parameter gamma to infinity, this leads to shift invariance of the residuals. So I have this parameter beta infinity, which gives me shift invariant residuals. This is not the causal parameter, but I call it diluted causal because it still leads to invariant shift invariant residuals. Now, this leads somehow to associations of different type. There's marginal correlation between variables. This can be very spurious. There's regression. This is partial correlation. That's better. Now we say, well, maybe you should go for diluted causal for invariance, and at the inner ball are the true causal associations, which are very hard to get at from data. And let me use the last 2-3 minutes to just show this a bit in place. First, I would like to quote John Tukey, who kind of made already the first step here. Tukey wrote in 1954, one of the major arguments for regression, for the green area here instead of correlation, is potential stability. We are very sure that the correlation cannot remain the same over a wide range of situations. It will not be the same over a wide range of subpopulations, but it is possible that the regression coefficient might. We are seeking stability of our coefficients so that we can hope to give them theoretical significance. So Tukey stabilized into the green area, and we go one step further to the blue one. We use this actually to kind of understand better the cholesterol pathway. This was an exciting project with Rudi Ebersold, who is a world expert on measuring proteins in living systems simultaneously. And we tried to understand the cholesterol pathway better in terms of this diluted causal parameter, in terms of this beta infinity parameter. I'm skipping the details here, but what you can do somehow is you can look at prediction potential versus invariance potential. And if you claim invariance to be more important, you would say these proteins actually turned out or are potentially important for the cholesterol pathway. And the point again is we have a certain validation in a certain metric where we can argue that invariance is a better procedure than just looking at prediction regression association alone. The story would go on. We have other applications in the life sciences, and let me conclude. Interpretation, causality, and robustness, they're related to each other, at least in the outline framework of causality and robustness. The point of stabilizing and finding suitable invariances in large data sets, it's really a very powerful thing. It can make a relevant difference in practice, and actually, I believe, in the context of very many mathematical models. Lastly, we hear nowadays quite often about causal AI. I think this is an overly ambitious word, and truish causality is very far away. But in fact, if you look what causal AI does, if you look into these contributions, it is mostly about robust and reliable prediction. Thank you very much.